Good morning. Now let us see combination of lens. So in the last class we have an equation. We got an equation 1 by f is equal to 1 by v minus 1 by u. That's our thin lens formula we obtained along with the lens maker's formula. So here we have two lenses, and what we are going to do today is a combination of lenses. If we combine the two lenses, how it behaves, like what is the magnification it gives, and what is the power of the two lenses together, and what focal length they give together. That is what we are going to discuss today. So these two lenses having different focal length f1 and f2, the two lenses L1 and L2 having focal length f1 and f2, we keep together, and an object is here. Light from the object first passes through the lens L1, then it passes through L2, and a final image is formed here, I, at a distance v from the center of the two lenses. So let the object distance be u, and the object distance is measured from the center of the two lenses. And as we told in the last class, the first lens L1, this produces an image. We know this is a convex lens, so it has to produce an image. That image is at a distance v1, and that image is I1, which is a virtual image. So this is a virtual image created by L1, and this virtual image acts as object for the second lens L2, and the L2 lens gives an image I at a distance v. So this is the situation for the first lens L1 having focal length f1, that creates an image I1 at a distance v1, and that image, virtual image, acts as an object for the second lens L2, and that lens L2 gives an image I at a distance v from it. Now applying the lens formula, thin lens formula for the first lens, we get 1 by f1, the focal length is f1, so equation is 1 by f1 is equal to 1 by v minus 1 by u, but here v is v1 because image is here. The first lens creates image here I1, that image distance is v1, so we have 1 by f1 is 1 by v1 minus 1 by object distance u. That's equation number 1. Now for the second lens, we told for lens L2 having focal length f2, object is this I1, this virtual image is the object for L2, and I is the image, which means object distance is v1, image distance is v, and focal length is f2. So applying equation for the second lens, we get 1 by f2 is equal to 1 by v minus 1 by v1. So this is the image distance, this is the object distance. So we got two equations, one for first lens L1 and the second one for L2. Now we know that these two together act as a single lens. If so, that lens will have a focal length f. Together they will have a focal length f. And for them, object distance will be just u, and the image distance will be final v. No v1 or I1 image, nothing happens when they are treated as a single lens. So for that lens, we can write the equation 1 by f is 1 by v minus 1 by u, where v is the final image distance, u is the object distance, and f is the focal length of the two lenses together. Together, what is their focal length? So that is what written here, 1 by f is equal to 1 by v minus 1 by u, where this f means the focal length, effective focal length of the two lenses together. Now as I said, we have two equations, equation number 1 and 2. If we add the two equations. Equation number 1 and 2 we get add, that means 1 by f1 plus 1 by f2 we add. RHS also should be added, 1 by v1 plus 1 by v minus 1 by u minus 1 by v, all these terms are added. So now we get 1 by f1 plus 1 by f2 is equal to 1 by v1 minus 1 by u plus 1 by v minus 1 by v1. So here minus 1 by v1 and plus 1 by v1 get cancelled. Here is 1 by v and minus 1 by u, that is 1 by v minus 1 by u is 1 by f1 plus 1 by f2. So here RHS we got 1 by v minus 1 by u, and we told if we consider the two lenses as a single lens that has a focal length f, and the equation becomes 1 by f is equal to 1 by v minus 1 by u. Now we are getting on the RHS same 1 by v minus 1 by u. On the LHS we get 1 by f1 plus 1 by f2. So comparing these two, it is very clear that 1 by f is equal to 1 by f1 plus 1 by f2. So that is written here, 1 by f is equal to 1 by f1 plus 1 by f2. Now we know that reciprocal of focal length is the power. We have the definition for power, which is the reciprocal of focal length. So this is power of the first lens, this is the power of the second lens, and this is the total effective power of the lens together. So the two lenses together, their power is P. Power of first lens is P1, power of second lens is P2. So this is the equation for the focal length when two lenses are kept together, and this is the power equation. This is for two lenses, two convex lenses. If one is convex, other one is concave, proper sign convention should be given. For focal length of convex lens as positive, focal length of concave lens as a negative. Now one more term we need to analyze, that is about the magnification. Magnification is the ratio of image distance to object distance. That is m was equal to general equation v by u. Now for the first lens, let's take the magnification separately for each lens. For the first lens, we told the first lens object distance is u, image distance is v1. So here for the first lens magnification, if I write m1, that is image distance v1 by object distance u. Similarly for a second lens L2, we can write the image distance as v and object distance as v1. So let us write m2 as v by v1. And we know that if they act as a single lens, they have only a one single magnification, that is m, which is the final image distance divided by the object distance v by u. So m1 is v1 by u, m2 is v by v1, and together magnification is v by u. Their effective magnification is v by u. Let's check out these equations again. We have m1 and m2. If you multiply this m1 into m2, we multiply m1 and m2, we get v1 by u into v by v1. So v1 cancel, we get v by u. Just now we told v by u is the effective magnification. So effective magnification m is nothing but product of magnifications produced by individual lenses. So three terms we told. One is focal length, how they are affected, power, how it is affected, and the magnification, how it is affected. So these are about a combination of lenses.